Good morning, everyone, and welcome to Friday's lecture. Some of you may be seeing this beforehand. Again, I apologize. I had to travel for some family matters this Friday, and I'm not able to do the lecture synchronously. Where we're going to pick up on today and sort of wrap up our discussion of volcanoes is talking about the role of volcanoes in society. We've talked about volcanoes, how they're formed, their geological setting, and some of the geological hazards they can impart on society. But I wanted to sort of talk about some of the history related to volcanoes. Volcanoes have been really prominent in terms of various aspects of society related to art, related to major political changes, and related to, in many cases, mass extinctions throughout the global history. So a few examples of this, for relevance, we mentioned the idea that ashfall can often lead to major crop failures, and in many cases, those crop failures can cause political and social unrest, and even leading to revolt. Many folks today would believe that the French Revolution is actually caused by a variety of political and social aspects leading up to a scenario where an Icelandic volcano, much like the volcanoes that caused the loss of airline travel in 2010, led to a period of intense cooling, crop failures, and actually pushed the French Revolution past the point of no return, and led to major changes in society. On that topic, there's also examples throughout Earth's history. We talked about the mass extinctions earlier in the semester, and particularly the Permo-Triassic mass extinction, which is the largest known mass extinction in Earth's history, or at least recorded in Earth's history, is thought to be related to a lot of volcanic activity, basically the formation of something called the Siberian traps, or a large igneous eruption in what's now northern Russia, which led to major changes in global temperature through stratospheric dust, and changes in the amount of SO2 and CO2 in the Earth's atmosphere. A lot of that's still heavily debated, but the point here is that we understand how much volcanoes can actually influence the history of life on Earth. I want to spend a little bit of time talking about their more relevant roles in society. So, without bringing anything new here, just bring up some of the ideas we talked about before. There's sort of some key ways that volcanic eruptions can influence global scale or regional scale societies. The most important, I would say, or the most common, is the release of ash, sulfur dioxide, and hydrochloric acid, with significant enough force, basically with one of these vertical blasts, for that material to reach the stratosphere. And once that material reaches the stratosphere, which is the area that's not, the troposphere is rapidly mixed. That's where the weather occurs, where things can get sort of filtered out and back to the Earth's surface really quickly. The stratosphere actually, by comparison, has relatively lower amounts of mass density. The dust, the material that gets there, can take quite a long time to actually get back into the troposphere. There's a rapid mixing at the top of the stratosphere and troposphere, but that boundaries is not mixed very efficiently. And as a result, material that gets to the stratosphere can have really long-term implications for forming clouds, blocking radiation, and things like that. So the key vector here with this eruption, if it's a vertical and puts ash and material into the stratosphere, is that can form what we call cloud condensation nuclei. Basically, that material can allow water and other water vapor to sort of congeal around it, and basically that will change the Earth's libido, change the likelihood that the albedo will be increased, where that solar radiation comes in, when it will be reflected back off of that, reaching the surface of the Earth. In that scenario, the biggest implication of those stratospheric dust is a pronounced episode of global cooling. Okay, so if you think about global warming, we talked about carbon dioxide sort of providing a blanket that keeps the radiation, thermal radiation that reaches the Earth and bounces back into the atmosphere contained within it. This is sort of the opposite effect. This is the other side of the blanket, if you will, where it's reflecting the heat out before it even gets into the Earth. And as a result, volcanic events lead to major stratospheric injections of material, can actually prevent radiation reaching the Earth, and as a result, keep the Earth quite a lot cooler. Now, this can come in a variety of forms: ash, debris, sulfur dioxide, and hydrochloric acid are the most important. Importantly, two of these three, so sulfur dioxide and HCl, can actually interact with cloud vapor and materials like that, and actually actually increase rain events, increase the acidity of rain events. But really, the dust themselves can actually, even without forming cloud nuclei once it reaches the stratosphere, can actually just help prevent, or not help, but can prevent radiation from reaching the surface. And there are a whole variety of other heterogeneous chemistry that can occur that can result from interaction of those things. Once those materials are in the troposphere, they're really important for making clouds, but mostly in the stratosphere, the dust is the main actor. Key things here as well, all these materials keep the infrared heat, within. It prevents heat from actually getting into the Earth's cycle. So I mentioned the French Revolution. This is a scenario where, for those of you who follow history, and I don't have all the history at the front of my brain at all, but there was a lot of political unrest. There was a desire to have democracy, to move away from a monarchy, and basically the economy started to experience some struggles. What really put this to a tipping point, and I'm butchering the explanation of the history, is a volcano in Iceland, in the Krafla area, that saw one of these major eruptions, had a vertical ash fall, and that ashfall debris did a few things. One is that debris blew over, just like the Mount St. Helens blew to Ohio and Pennsylvania. That ashfall blew into Western Europe. It, for starters, was deposited on this isn't France, this is actually Iceland, but deposited on the surface, leading to some of the factors we talked about, like tree, crop, plant damage, denudation of plant material, and basically a cycle of crop death. That, of course, put the poverty and hunger into the forefront of folks' mind, and sort of pushed the social unrest beyond a point of no return, where there's a critical tipping point. And actually, many scholars credit this volcano for being the event that sort of was the straw that broke the camel's back, if you will, and created the French Revolution. That's not by any means an only example of this. Many of you may have heard of the year without summer. This is in 1816, where there was snow on the 4th of July in the city of Boston. So this is only 204 years ago now. And that was related to the Tambora volcano, which actually ejected about an incredibly large 19 cubic miles of ejecta, or ashfall, that went all over the Earth. And notice that's nominally 80 times bigger than Mount St. Helens. And that material led to the same exact scenario we just talked about, where the material gets ejected in the troposphere and around, affects vegetation, but most of the impact is by the fact that material and chemicals gets into the stratosphere, where it can form, increase the albedo and block radiation from entering the surface. In this scenario, this is broadly in American literature. It led to a lot of paintings about the poverty during that time, and hunger during that time. But it was a really influential period where there was crop failure as far away from Tambora as there is in Boston, as far away from Tambora as you could possibly imagine. So, just for some perspective here, Mount Tambora is over here in Indonesia, eastern Indonesia, and basically the Tambora volcano, this is today, a relatively large volcano, erupted about, again, 20 cubic miles of ejecta. And this kind of goes back to the idea of the role of the Pacific Ring of Fire in terms of creating volcanic hazards. So this is something quite profoundly far from North America. This is the idea of the dust cloud that was released from the Tambora, and you can see that it wasn't just areas like Boston or Northeastern United States that are influenced, but actually this dust fall led to a year without summer in most of Europe and in Northeastern United States as well. So, what's happening at this time? This is actually relevant for a lot of aspects of Ohio. This is a period where Ohio just started to be, experienced a lot of population growth, people moving from Massachusetts and other parts of New England to the area, and that was rapidly exacerbated as people tried to move away from the Northeast, where there was snowy winters even in the middle of summer. So this is quite prolific in literature. There's quite a few paintings that are about this. A lot of them focus on the bright red sky, or the death sky, or blood sky, if it's called different ways. And most of this is based on the fact that material that's ejected into the stratosphere actually causes it works with the same phenomena as the dust that you see at sun up and sundown cause that sort of bright orange sky behind you. As a result, and particularly in European and American literature at the time, um, this became a pretty common theme to have these bright, vivid red skies, which actually over years, when the stratus material sort of mixed out of the stratosphere, it was washed, was washed away, and we saw less of this bright red sky outside of the beginning and end of the day. Most of that red sky that you see is actually caused by the fact the sun's penetrating through, as the sun's going down, it's penetrating through a very longer length of the sky, if you will. And as a result, we see enough refraction of the light to get the red hue in sun up and sun down. It's actually the fact that even though during the peak of the day, you get the same effect if you have more and more material, more particles in the same volume in a smaller volume of air. So that's why that was seen throughout the day. You can see this in a lot of the literature, paintings, etc. And the other phenomenon that's really popular from that time frame is, of course, the fact that there's a lot of gray skies and not a lot of sunlight because of the abundant sort of cloud condensation nuclei keeping the clouds forming and sort of blocking the sun. So, tangibly, this affected economies in North America, the Middle East, Europe. It certainly affected crop growth for that year, not just because it was cold, but also because the ashfall actually changed the sort of ruined vegetation and crops. In the long run, it's actually has some peripheral benefits, right? It actually adds a lot of nutrients to the soil and items like that. But by and large, this is something that had a globally profound effect, where people, here, of course, in Massachusetts, look at the dust and have no idea where it came from, assume it would have to be the wrath of God. And the folks near Tambora obviously saw a much more dramatic and horrifying event. So this type of scenario is not at all uncommon. I should have said that in addition to those factors, the other factor, of course, is the fact that temperature is decreased, in that case by about a degree and a half globally, which is another part of, in addition to the caused by the higher albedo and less radiation making it into the Earth, which led to a global cooling effect that changed the temperature for a few years. This is an example from Mount Pinatubo, from the Zambales region of the Philippines, and this is an example of the volcanic lake that's left behind after there's been this major catastrophic eruption. But this is Pinatubo. Again, same scenario: major stratospheric ejection of dust and debris. This is a photo I just really love. You can see somebody driving down the road as this finally actually starts to go off, and you can get the clear impression this person either didn't survive or didn't have a very good chance, or was pretty darn lucky if he or she did. Similar to what we saw in the Mount St. Helens discussion, a very big vertical and lateral blast. But in this, luckily for the folks in the Philippines, dominantly Pinatubo was a vertical eruption that led to pretty catastrophic disruption in the space of the area. This is an example of Pinatubo erupted in, I think it was May of 1991, but 1991 for sure. And this is obviously before most of you would be born, I guess. But this is a period where in the late 80s, the early 80s, late 80s, we're actually in a relatively cooler period compared to now. Obviously, climate change has decreased temperature in recent times. But this actually is noted for causing about a 0.5 to 0.6 degree temperature drop just as a result of this one instantaneous event at Mount Pinatubo, where just the dust that made it, this dust wasn't really observed, on a global scale. It was clearly there was dust fall recorded in ice cores in Antarctica and Iceland, but at very minute levels by comparison to what we'd see from something like Tambora. But what was observed is that it was about a 5 or 6 year period directly following the eruption of Pinatubo, where there was a global decrease in temperature of about a half degree Celsius. Now this brings up some bigger questions and some bigger ideas here. Obviously, we recognize the release of sulfuric acid, of SO2, hydrochloric acid, and dust into the stratosphere clearly has an impact on climate, right? This is is a major aspect of the volcanoes, providing material that increases the albedo and decreases the temperature of the Earth by letting less solar radiation reach the Earth's surface. What I want to call your attention to is that this process goes on continuously all the time. It's one of the main mechanisms by which Earth regulates the temperature of the planet. So preventing the radiation coming in is a major climate forcing effect. And in reality, the volcanoes do this sort of, just like earthquakes, sort of cyclically all the time. There's obviously locations around the Pacific Ring of Fire where this is more common, but reality is we can't really control these as a climate forcing vector. Another competing factor to this that I want to make you aware of around volcanoes is the fact that volcanoes have three major volatiles that are most abundant in their eruptions. So number one is actually water vapor. It's a major aspect of water degassing from the mantle, but isn't a major climate forcing effect on the aggregate. But the other two components, the SO2 and the CO2, actually are the next two most abundant gases released during volcanic eruption, CO2 being second and SO2 being by far the third compared to the water and CO2. The thing here is that CO2 actually builds up in the troposphere during periods of major volcanism. And that actually, as you'd expect, similar to CO2 released by anthropogenic activities today, leads to a scenario of potential for global warming. So there's this delicate balance between the CO2 that's continuously released by all volcanoes, which whatever amount of CO2 that's released will reach the troposphere and can cause relative global warming, and that's balanced by the frequency in which we actually see these pyroclastic eruptions, particularly vertical pyroclastic eruptions that can release debris directly into the stratosphere and cause pronounced global cooling. The reality is that all these things, sort of compete with each other and cause the modulations and some of the climate fluctuations we see. It's not in any way enough to account for the global warming related temperatures from CO2 emissions by anthropogenic sources, but on that sort of climate scale throughout history, there have been major episodes or swings of temperature from global cooling to global warming that are modulated by factors such as mass extinctions from exogenous things like meteorites, activities related to volcanoes, clearly, major changes in life, adding oxygen to the atmosphere and things like that also play a role. But I wanted to highlight this in terms of the volcanoes, that these can, at any moment when we see an eruption like this that allows material to get in the stratosphere, we could see a degree or half a degree of temperature modulation just by that alone. And we'll come back to this a lot later in the semester when we talk about the global climate cycle and the anthropogenic role in climate change. But what I wanted to highlight for you here is this is a pretty common phenomenon throughout geological history. But the most clear example of this is actually related again to the Siberian traps, which occurred about right around the time of the PT boundary or the Permo-Triassic boundary around 252 million years ago. And it's thought that the combination of really high CO2, high amounts of ash, and high amounts of sulfur dioxide all contributed to the demise of life on Earth at that time. So, ranging from wiping out 95% of life to catalyzing things like the French Revolution and graphic orange-colored sky themes in paintings. Clearly, there's a fairly important role and link between society and volcanic hazards, specifically as it can cause major devastation and global climate change. So this is an example. This is just in the last few hundred years, really, I guess, almost 800 years, I guess. But these are just a map of the major volcanic eruptions that sort of changed the world. So you can see these various ones, particularly Indonesia has been a bad actor. There's a lot of perfect combination of a very active plate, a very active subduction zone, convergent subduction zone that leads to a lot of composite volcanoes, tend to be higher silica content. And as a result, those higher silica content volcanoes are more prone to major pyroclastic and explosive events. So the suite of volcanoes all along this Pacific Ring of Fire, where there's subduction, oceanic subduction beneath the continents, or oceanic subduction, they're more prone in general to having a higher silica content, more likely to have higher silica content, more prone to having explosive eruptions. Some of the key ones in New Zealand, Vanuatu, Kauai in Vanuatu, and then all of the string of Indonesian and Philippine islands. Many have seen major eruptive events, Krakatoa, Tambora, Pinatubo in the Philippines, that have actually produced major, sulfate or SO2 aerosol injections in the stratosphere that led to pretty pronounced cooling episodes. It's not only the Pacific Oceania region that's a culprit here. There are major volcanic eruptions like this in the Andes region of the western margin of South America, and also in the Aleutian Islands up here Pennsylvania travels on the mind, up here in Alaska in the Aleutian Islands. And Laki, which is actually in Iceland, is sort of outside of the realm of what normally releases a lot of stratospheric material, but in that particular case, it was highly explosive eruption, and actually it was noted to cause some accretion of stratospheric material. But Laki, the main one there, is of course sort of becoming the tipping point of ash fall in France and other parts of Western Europe. So these give you a perspective. This is recorded by Southern Hemisphere, Northern Hemisphere. It seems that most of the big actors have been the ones that are just happen to be north of the Northern Hemisphere. Doesn't necessarily matter very much in that regard, but these are all events that contributed major volumes of sulfate aerosols in the stratosphere as a result of the eruptions, and the biggest of which is thought to be related to Rinjani back here in Krakatoa in this region back at largely in Indonesia, have been the major climate forcers. If you think about this in terms of the Dark Ages and the sort of mini ice age they call it, there's a period in Northern Europe in particular, in the 1200s, the 1400s, where you saw a major period of global cooling. They called it the mini ice age. It wasn't really an ice age, but it was extended periods of cooler times, and those are actually tied to this cluster of major stratospheric events during that time. For perspective, here's the eruption of Tambora here. You can see that's a major forcing event led to cooling in the Northern Hemisphere, and there've been other bigger ones. More recently, Tambora in 1815 that caused a lot of cooling events. So we talked a lot about the hazards tied to volcanoes to this point in the class. I wanted to bring up for you some of the positives. We tend to think about when we think about sustainability, we tend to think about population growth and population needs, and as a result, hazards kind of comes to bear. And we think about environmental geosciences as a major influence on society in a lot of directions. But one of the things I want to talk a little bit about while we're on the topic of volcanoes, and we'll come back to this in more detail when it comes to energy, topics of energy later in the semester, is some of the benefits we get from volcanoes. One of the things that you see, particularly in areas like the Philippines, Indonesia, Central and South America, is that in these areas where there's extensive chains of volcanoes, we've developed really quite a profound amount of renewable energy. Places like the Philippines and Indonesia get as much as 30 to 40% of all their energy demands, in some cases much more of their energy demands, by utilizing geothermal energy resources. And as a result, what basically is happening there is that most of the ways we make energy or make power in the United States and in the world is by making steam conversion, using steam to turn a turbine and use that to derive electricity. And in essence, the geothermal energy is not very different than that, except for rather than trying to burn something like wood or coal, what we're doing is using the direct geothermal heat that's in these magmatic or volcanic systems, particularly again in Indonesia and Philippines. These are really abundant sources of energy. And in many cases, we can actually utilize the steam from those volcanic systems by sinking a well and letting it spin a turbine. In others, we can actually take and pump seawater or fresh water and recycle it into the reservoir and allow that to make steam for us to run the power plant. So we can sort of engineer geothermal systems that we can inject water and keep the process going by, not by providing more heat, that's provided by the magma or lava, magma in the case of geothermal systems. I apologize. But the reality is that many of these systems become depleted in water eventually. If you pump the water out, steam is released. It takes a long time for groundwater to percolate down into these systems, and we have developed a lot of systems around the world where we can inject water into the subsurface and actually increase the energy yield from them by these injected geothermal systems. So these are done in pretty broad fields where you'll put wells across a couple kilometers, maybe a couple dozen kilometers, often have well insulated pipes that are going to run this water, or steam, and basically bring it to a plant where we can be it can be cool, use the spin the turbine and cooled and dissipated as water. So today it accounts for a significant percentage of energy in many countries. In the United States, we still use geothermal where it's available, and we do derive a few percentage of our domestic energy consumption from geothermal energy. Clearly today, as we're trying to decarbonize the world, use less fossil fuels, there's a growing interest again in using geothermal energy, much like there was in the late 70s when the Iran oil crisis became a prevalent issue and the price of oil and gas went up. Today, it's not really economics driving; it's more concern of providing a low carbon energy source. Additional benefits besides geothermal energy is that these volcanic systems often provide really important and key critical resources, or strategic minerals, some people call them. So, epithermal gold and copper and zinc deposits where you see hot steam that was produced naturally in those geothermal systems will leach metals that are insoluble from the rocks, and actually those materials can migrate with those hot fluids up to the point where they cool down, and they sort of mineralize. They can crystallize with sulfides. Sometimes it crystallizes in quartz minerals, but in many cases these are major deposits of gold, silver, copper, zinc, and other precious metal ores that are mined for various purposes. Used in metallo drugs, used in circuitry, wiring, catalysts, you name it. Modern society depends on it, and in reality, most of these resources are actually accumulated in either present or, in many cases, extinct volcanic systems. There are other metals that such as mercury, which everyone heard the story of the Mad Hatter. The reality is there's a whole history of Mad Hatters where they used to use the steam from fumarole vents near volcanoes to fit hats, but part of that issue is that the mercury they used to form the hats actually caused them to go crazy, hence the term the Mad Hatter, which was popularized actually, I believe, in Danbury, Connecticut, in the United States, but is relevant to the story of long-term people who used volcanic geothermal systems to fit felt hats and things like that, and were exposed to mercury in the process. So this is an example of azurite, which is a major copper ore, and I don't know if anyone, obviously we're not doing this synchronously today, so I'm not gonna. This is a rhetorical question, but if anyone can identify this particular type of rock, this is actually pumice, and many of you may not really probably remember seeing this in school at some point. It's very light, lighter than air, it floats in water, but actually it has a lot of economic interest as well. A lot of people crush this and use it in things like soaps. They use it in filtration systems and things like that, and as a result, there's some industrial implications, largely though around soap, tied to these things. So you do commonly see these deposits being mined as a resource. The picture down here at the bottom is actually one of the most common reasons we mine volcanic materials. It's actually iron ore, and the iron ore is iron is very abundant, relatively speaking, in mafic minerals. So sort of a high temperature, quickly flowing, low silica basalts often are rich in iron, and as a result, volcanic systems that had abundant amounts of minerals called olivine and pyroxene are sort of explored for as iron ores in areas near volcanoes. So in all, it's a location where we tend to see recycling of materials that are not common on typical crust of carbonate minerals and things like that that are often mined for various resources. And then really the most abundant, broadest, biggest impact of in terms of benefits of volcanoes is that we talked about the fact that dust and ashfall can be transported great distances around the earth. It can cause global cooling, can kill crops, and episodically cool the temperature of the earth quite dramatically and sometimes even catastrophically to society. But on the aggregate, the next year, if you will, when this material sort of rains down, gets incorporated into the soil, it actually provides a really important amount of nutrient loading. So critical elements like iron, in particular, are often very quickly utilized in soils by plants. And at some level, there needs to be a replenishment of those critical metals or essential metals in order to sort of catalyze fertile areas. So, both thinking about this in terms of very episodic windfalls, that of course brings nutrients out to areas that don't normally have it. But what you'll also observe is that areas near volcanoes where these pyroclastic flows and ash deposits are prevalent, you often find very rich soil. It's often very commonly utilized to do sort of high nutrient demand foods, things like coffee and which are obviously also dependent on the climate being wet and warm and things like that. But importantly, these are often very rich soils. You'll often see, in particular, a lot of vineyards and whatnot in areas where you have these rich soils because it provides a lot of flavor and a lot of bold flavors into the wine and into the coffee as well. So the other benefits are not just ore deposits. It actually creates really important nutrients for soils and agricultural crop growth. Lastly, it sounds a little silly thinking about this in terms of environmental geosciences, but one of the major economic benefits of volcanoes is they often are areas of major tourism, major agritourism. So I won't spend much time talking about that. You all get the idea. Someplace that's near the water or near the montane volcanoes, and particularly if there's some activity, it can be of quite interest to a lot of people. But there's significant economic benefits, and people are often very interested in understanding geological hazards near these areas. I spent a good part of my 20s traveling around Africa and Italy, evaluating geological hazards in areas where people are building tourism sites and parks and things like that near these areas, not just for tourists, but it's a clear implication of some of the activity that goes along with the volcanoes. So, we spent a lot of time talking about the hazards. It's certainly not all bad. There are clear benefits, but I don't think we can understate the profound effect that volcanoes have on society. So with that, I'm going to just sort of recap the key things about the volcanoes. Remember, volcanoes are generally located near plate boundaries. Clearly, the highest concentration of volcanoes along the Pacific Ring of Fire. Most importantly, if you think about this from a hazards perspective, the biggest mass, on a volumetric basis or mass basis, the biggest amounts of volcanoes are in divergent plate boundaries near mid-ocean ridges. But the reality is, in terms of the volcanoes that influence society, both by causing tsunamis, by leading to major eruption hazards, and/or providing some of those benefits, are either island arcs of oceanic subduction or oceanic continental subduction around that Pacific Ring of Fire. That's where most of the volcanoes are. That's as a result of where most of the volcanic hazards are. Some key terms, although I suspect you probably know this. Remember that magma is a molten rock with a range of viscosities. Once it gets to the surface, it's called lava. But the key thing here is that the hazards, the mobility, the resources, everything that's going to be tied to the characteristics we can derive from that magma, go back to understanding the range of viscosities and the silica content. The silica content and the temperature at which that magma body is formed and brought to the Earth's surface largely dictates the hazards, the minerals that are present, the likelihood of the gases and volatiles causing major issues. We talked about the different types of ways magma is formed. All the heat in the Earth, again, goes back to the earlier parts of the lectures earlier in the semester, are derived by latent heat trapped at the formation of the Earth, some amount of crystallization, but really the driver of this is going to be radioactive heat, heat produced by radioactive decay, uranium, thorium, potassium. But even still, given the immense pressures of the Earth's plates overriding the Earth's mantle, magma is really only formed as a melt in areas where we remove that pressure and allow decompressional melting to bring the material to a liquid and make it more buoyant, bring it to the surface, or by the addition of volatiles, so removal of water and carbonate minerals, CO2 and such from the subducting slabs what allows magma to be generated. We cover that a little bit, and that might sound like it's not terribly important, but I bring to your attention again, as far as we know, the Earth is the only place we've identified life so far, but one of the more interesting philosophical things about this is that it's also the only place we've seen sustained plate tectonics. So the way we can generate a melt initially by getting enough things hot is pretty easy to do. The way we can sustain that over a 4.5 billion year lifespan of the Earth, still a pretty open question that's not identified anywhere else we've looked so far, or anything else we've been able to see so far. So as a result, keep in mind that in our planet, the two ways we most commonly see that occurring is decompressive melting, where divergent plate boundaries allow pressure to be reduced and things go from the solid to the liquid, which is called crossing the solidus. Decreasing the pressure makes it behave like a liquid, or the addition of volatiles that can cause the melts to occur. In all cases, these are the main drivers. Obviously, mantle plumes are another example of the way we can drive a magma. I think it can't be overstated enough. Volcanoes have a profound effect in society in both the positive and negative way. Clearly, a variety of hazards from lava flows, harmful gases, ash falls, and even tsunamis can have a great influence in a lot of areas. The major global scale things are usually tied to ash falls and/or the introduction of material or chemicals into the stratosphere, which can have profound cooling effects. Many examples throughout society, we've seen things like little ice ages, winters, summers without years without summer, snow in the summer in the northern hemisphere, caused by non-localized or actually often very distant volcanic eruptions that put material into the stratosphere. But I also just want to close by saying on volcanoes, don't underestimate the profound benefits, particularly related to ore deposits, the introduction of critical minerals and critical metals, as well as the value of making a fertile soil, which is important for agriculture. So the benefits and the risks and the hazards are all part of the package. But all in all, volcanoes dictate a lot more of our lives than probably we've ever realized, at least not on the day-to-day basis, perhaps, but on the sort of millennial scales. And the range of the impact on society can be from, bringing Earth to the brink of ending life in terms of major mass extinctions, all the way to creating a little ash debris to wash off our windshields, or a atypically cool summer. So, and all in all, stay tuned. If you look at the cycle of mountains that affect the Earth, you might have been born late enough to not remember Pinatubo, probably war, but somewhere in your life there'll probably be another volcano that'll come off, and you'll get a couple of atypically cool years from these processes. Once again, I apologize I had to do this last lecture for Friday asynchronously. I'll look forward to seeing you all in person on Monday. This week's worksheet is due by 11:59 p.m. tonight, and just remember, on Sunday next week's worksheet will be posted, and next week we'll move off of geological hazards related to plate tectonics and move on to coastal processes and get into some water related topics for a little while. So thanks for listening, and again, apologize I couldn't do this lecture synchronously. Have a great weekend. Bye.